Welcome to my YouTube channel. In this video, we are going to be looking at how to calculate the magnetic field along the axis of a triangular loop. This is a triangle that we are interested in, and the point that we want to calculate the magnetic field is along the z-axis, where here is the y-axis, this side is the x-axis. Now, this triangle is an equilateral triangle of sides A, and A. We aligned this triangle in such a way that the x-axis will be along this side, the y-axis will be here, then the z-axis will come out. So at any point along this z-axis, we might be interested in calculating the magnetic field at that point. Now, to calculate this, we'll use the Bell-Savart law, which we are going to see in the next slide. But for now, let's analyze this triangle and see how it goes. Now, this angle from this side to this side is 60 degrees, so half of it is 30. Now, from our analysis, trig analysis, this side to this side is given as a over 2 times 30. You can always confirm that. Okay, so we take this side as our zero axis. This side will be a over 2, and this side will be minus a over 2. Now, what we want to do is to calculate the effect of an elemental change at any point along this axis, and that point we can transfer it to this point. If you notice, we can pull out the z-axis outward, then link this particular point to that z-axis, and as a result we get this particular diagram. So from this diagram, you notice that this side is just this side, while this side to this side is from this side upward to meet the z-axis. You can see from here to here is as a over 2 minus a over 2. Now this side is my y-axis and this side is my y-axis. Then outward, the line pointing outward is my z-axis. So now that we have this and we're able to show that this side is a over 2 times 30, what we now want to do is to find the magnetic field at this point as a result of this small element. Then by the time we integrate, then the entire length of this one will now be the contribution to that particular point. Okay. Now, this is the formula we are going to be using, which is the Bell-Savart law, where I is the current flowing through the triangular loop. R is the vector that I was showing to you in the previous slide. Now, we have the first segment. The first segment is the length that is parallel to the x-axis. So we have our dl is equal to dx, because that length is parallel to the x-axis, so our dl is equal to dx prime x cap. Then our r is given by this z plus this plus a over 2 times 30. If you recall that our z is the one coming out of it, our x along that particular direction, then this expression. Hence, to determine these parts, we'll just take the magnitude of this, which will give us z squared, x squared, and everything here squared, which will give us this. But meanwhile, our dl is equal to dx prime dx. This expression here, this symbol here, is called the cross product. Cross this expression, which is our gamma, our r vector, which is this expression. Okay, so in this next slide, we multiply 3z by that expression that we have in the previous slide. Now, the reason is because we have 3 lengths of the triangle. So because they are highly symmetric, we use 3 multiplied by z, where this z is pointing towards the z direction. So when we cross the product, when we cross the 2 expressions at the top, will result to this. Remember, x cross x is 0, x cross y is z. So if you follow that same pattern, you get this expression here. Finally, at the bottom, from here, we'll bring out all the terms that are constants, that are not dependent of that are independent of the integral. So I4 pi will come and meet this. Then this our z is this dot here is a dot product. So z dot y will give me 0, z dot z will give me 1. So at the end of the day, we derive this expression. We arrive at this expression. So this expression remains at the bottom. Now we are going to be integrating from minus a over 2 to a over 2. Recall that this one is independent of x, so you bring it out and you have this expression. This expression here, will represent it using a constant k. We now have this expression. Also, this expression here, we can represent it as t squared, which we'll see in the next slide. Now we have let t squared equal to this expression, and let all this expression equal to k, which is this k. So by the time you substitute, you have this expression. From here, to integrate this expression, we say let x prime equal to t tan theta. So that by the time we differentiate this x, we have dx prime equal to t sec squared theta d theta. You substitute these two expressions into this, you have your t tan theta, your t sec squared theta d theta, which is here. Then inside this expression, you have t squared. X prime is t squared t tan squared theta. So at the end of the day, it results to this particular one. And you can see that sec squared theta can cancel sec squared, leaving sec theta at the bottom. And sec theta is 1 all over cos theta. So cos theta will go up, leaving this one. T will cancel t, leaving t squared and this. So this one is independent of the integral sign. So we'll bring it out. It becomes k all over t squared, leaving cos theta d theta as this. If you integrate cos theta, you have sin theta. Then you now put in your upper and lower limit here. Now, but because what we have is our theta, we have to convert back from theta to this particular parameter. Remember that we have this particular triangle where our theta is equal to x all over, sin theta is equal to x all over this. Then we'll now have this expression. Sin theta is equal to x, cos theta is opposite all over adjacent. Then for sin theta, it becomes x all over this expression, which is this. Now our h is equal to k all over t squared. We substitute back. Instead of putting sin theta, we'll replace with this one, x prime all over this. So wherever we see x prime, we'll replace with a over 2 and minus a over 2. So k all over t squared remains this. Then our x prime is a over 2 plus theta squared minus a over 2 all over this expression. So if you simplify this, this plus this will give me a. This and this will come together as 1. So at the end of the day, we have this expression, which is a squared. So we substituted back the value of t into this expression. The value of t back into this expression. Okay, so from there we have this expression and this expression coming together by factorizing. Then we'll recall that 1 plus tan squared 30 is same thing as sec squared 30 plus z squared. So from here we'll move to this point. Remember that our sec squared 30 is the same thing as what? 1 all over cos squared 30. And cos 30 is the same thing as root 3 over 2. So if it is root 3 over 2, we'll square it and we'll square it. It will now be 3 over 4. I hope that's okay. So because we have 1 over 4 over 3, it becomes 4 over 3. Or 4 will take care of this 4, leaving 3 behind, plus z squared. Our k squared remains the same, a all over a squared all over 3 plus z squared. Now, what is the value of our k and the value of our t squared? We'll bring them into this place and here. Why this one is here? This a mod is this particular a. Multiply the initial a that came with the k. From this point, we have our hz equal to 3ia squared all over 8 pi, then tan theta. Then this expression is this. This expression is this. Recall that we can easily factorize. So we can easily simplify this one by saying a squared plus 3z squared all over 3. And that root 1 over 3 will come out here. Likewise, this particular one is z squared plus a squared all over 12. So at the end of the day, we are left with this expression. Or also take note, for this expression, our 1 over root 3, square root of 1 over root 3 will cancel tan 30, because tan 30 is the same thing as 1 all over root 3. So 1 over root 3 will cancel this 1 over root 3. So we have this final expression. This is now the magnetic field along the axis of a triangular loop. Now you might be interested in calculating magnetic field at the center of the triangular loop. So at the center of the triangular loop, z is equal to 0. And in so doing, this expression will reduce to this. So wherever you see z, it becomes 0. So you have a squared all over 12. Wherever you see z, it becomes 0. It becomes a squared. Square root of a is a. This a squared cancels this a squared, and you are left with this expression. Now 4 will go in 12, you have 3. 3 times 3, 9. 4 that went in 12 also divided 8, leaving 2. So at the end of the day, our h is equal to this. I hope this helps. Thanks. Like, share, and subscribe.